Moving on to amines. Now amines are compounds based on ammonia, which remember is NH3, but what you find is that the hydrogen atoms have been replaced with an alkyl group, so carbon and hydrogen, or aromatic rings, so we're building on our chemistry relating to benzene. Primary, secondary, tertiary amines. So the primary, secondary and tertiary refer to the number of R groups on the nitrogen atom. So if we start with ammonia, which we know is our core structure, let's draw the structure of a primary amine. And according to my definition, primary amine has one R group on the nitrogen atom, as we see here. What about a secondary amine? We're now going to have two R groups attached to that central nitrogen atom. And here's our tertiary amine. And then very closely related, we have our quaternary ammonium salt, which you're probably already aware has a positive charge. To reiterate, so amines we know are compounds based on ammonia, NH3, but the hydrogens in ammonia are replaced with either alkyl groups or aromatic rings. So our primary amine has a single R group attached, the secondary amines has two R groups attached, tertiary has three, and here's the structure of a quaternary ammonium salt. Now we're going to practice naming our amines. So here we have our core ammonia, one of our hydrogens replaced with CH3, CH2, 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 so we know it's a primary amine. What is the name of this? It's butylamine, due to the fact we've got 4 carbons. So we can see that the suffix amine is used when naming amines. Introducing an aromatic compound now, obviously benzene. So we have our core N. We've got a primary amine again, where one of our hydrogens this time is replaced with benzene ring. An aromatic ring in this case is given the prefix phenyl, so this is phenylamine. Now we've replaced a second hydrogen with an alkyl group. We've got 2 methyl groups, so that's why we need to write dimethyl amine. Dimethylamine. Our most complex structure now. Now remember that table I showed you, it's a list of functional groups in order of their priority. Now here we have higher priority functional groups present, and therefore the amine is given the prefix amino. So we need to look at our longest carbon chain, it's 3. With this carboxylic acid, it's propanoic acid. If I number the carbons, we've got carbon number 1, carbon number 2, carbon number 3. This OH from the alcohol functional group is in effect on the 3rd carbon. So in terms of naming, we're going to write 2 amino, that's this bit, 3 hydroxy, this portion, propanoic acid. And then a few extra points here. Because the amines are based on ammonia, we know that they have a trigonal pyramidal shape with bond angles of 107 degrees. Primary and secondary amines here can form hydrogen bonds due to the presence of that highly electronegative nitrogen. And due to those hydrogen bonds, they have higher boiling points than similarly sized alkanes, but lower than similarly sized alcohols. And that's because nitrogen is less electronegative than oxygen, so therefore the hydrogen bonds formed with primary and secondary amines are weaker. Short chain amines are soluble in water due to the formation of those hydrogen bonds, and unpleasantly, amines have fishy smells. Preparation of aliphatic amines using halogenoalkanes and ammonia. So the first thing you'll want to know is what an aliphatic amine is. These are amines that do not contain an aromatic ring. So no benzene. Now, primary aliphatic amines are produced by reacting halogenoalkanes with ammonia. What type of mechanism is it? It's a nucleophilic substitution reaction. I'm going to draw out the mechanism right now. So we'll take a halogenoalkane chloroethane, 2 carbons, there's the chlorine. We've said that we're reacting ammonia, so I'm going to pop that in here. Remember that ammonia has that lone pair. Due to the chlorine and the carbon, it will leave that carbon electron deficient. The chlorine will be electron rich. Our lone pair will therefore attack at this electron deficient carbon, causing the breakage of this bond. Let's add on that ammonia. Obviously, because that ammonia has the electron pair, it's acting as a nucleophile. But what happens next up is obviously we need to remove that positive charge on the nitrogen. So we need ammonia again, but in this case, the ammonia is going to act as a base because it's going to accept a proton in order to neutralize that charge. So there's our primary aliphatic amine. The name of this is obviously, we've got 2 carbons. I just taught you that we're going to add amine to the end as a suffix, so it's ethylamine. And then don't forget your salt product. Now, the primary amines produced can also act as nucleophiles, and this means that they can react with halogenoalkanes to form secondary amines via nucleophilic substitution. So we in effect take our halogenoalkane, the primary amine produced in the first reaction, and use the lone pair on that nitrogen to act as a nucleophile. So if we look at this nucleophilic substitution reaction, we've produced a secondary amine and a salt, and then the reactions continue with the secondary amine produced reacting with halogenoalkanes to form a tertiary amine. And then finally, those tertiary amines can react with halogenoalkanes to form the solid quaternary ammonium salts. Now, the result is a mixture of primary, secondary, and tertiary and quaternary ammonium salts, and we can separate these products using fractional distillation. And if we want to improve how much primary amine we produce, we should use a large excess of ammonia in order to force the ammonia to keep reacting to produce the primary amine, as opposed to moving through the secondary, tertiary, and quaternary ammonium salts. We can also produce primary amines through the reduction of nitriles. Now, primary alkyl amines can be prepared from halogenoalkanes in a 2-step process where the halogenoalkanes react with KCN in aqueous ethanol by nucleophilic substitution to form a nitrile. And then those nitriles can be reduced to primary amines using a hydrogen nickel catalyst. This gives a purer product than the halogenoalkane and ammonia method because you're not going to go through the primary, secondary, tertiary amine route. You're only going to produce the primary amine. However, a big disadvantage is that toxic cyanide is used. But look, here's our primary amine being made. Obviously, because of the cyanide containing the carbon, we're going to end up with a carbon chain of the amine where there's 1 extra carbon compared with the starting substance. Previously, we met this point in the specification, which was to do with the electrophilic substitution reactions of benzene. And what we did was we made an NO2 plus electrophile by reacting concentrated nitric acid and concentrated sulfuric acid. Remember, we said that the sulfuric acid was acting as an acid because it donates a proton. The HNO3 is acting as a base. Now, the result of that is it produces the nitronium ion, which is acting as our electrophile, so our lone pair acceptor, and we said it would react with aromatic rings. We're now going to build on that by stating that we can build aromatic amines, so amines which contain a benzene ring, such as phenylamine, through the following 3-step process. So step 1 is reacting our concentrated sulfuric acid with our nitric acid in order to generate our NO2 plus electrophile. Step 2 is using that NO2 plus electrophile and making it react with benzene according to the following mechanism. Here's our benzene ring, our aromatic hydrocarbon. Here's our electrophile, using arrows to represent the movement of electrons. Remember, we need to reform our delocalized electron system using electrons from the carbon-hydrogen bond. So there's the carbon-hydrogen bond. The NO2 joins here, and then our final product, because we lose that hydrogen, looks like this. And we have a spare H plus ion. So this is nitrobenzene. And then our final step, step 3, is to reduce our nitrobenzene to phenylamine. Again, something I've mentioned before, using tin and hydrochloric acid as the reducing agent. According to the following reaction, here's our nitrobenzene. The tin and hydrochloric acid form hydrogen, which acts as our reducing agent. And here's our phenylamine product. Now these aromatic amines, the aromatic, remember, because they contain a benzene ring, are used to manufacture dyes. Here's our nitrobenzene. Here's our phenylamine. Let's look at our overall equation. Always looking at the overview. This is how we make aromatic amines, so amines involving a benzene ring such as phenylamine. The first step, remember, was taking our sulfuric acid acting as an acid, the HNO3 acting as a base in order to generate our NO2+ electrophile. Here's the mechanism that I drew out showing the formation of nitrobenzene. Then we need to reduce that nitrobenzene to phenylamine using tin and hydrochloric acid, and here's the overall equation. So more information now. Amines are weak bases. Remember that you'll have that lone pair of electrons on the nitrogen that can attract a proton, and the strength of its ability to act as a base depends on the availability of the lone pair on the nitrogen. So alkyl groups release electrons towards the nitrogen atom, and this makes the lone pair on the nitrogens more available, so actually that makes them a stronger base, and we call this an inductive effect. Now secondary alkyl amines, ones containing two alkyl groups, are stronger bases than primary alkyl amines with one alkyl group, which are stronger bases than ammonia because they have no alkyl groups, and that's because the alkyl groups, as we've just said, release electrons towards the nitrogen. So obviously the more R groups you have attached, the more the electrons will be released towards the nitrogen atom. Ammonia with no alkyl groups will therefore be the weakest base. However, one thing to be aware of is that tertiary alkylamines are not stronger bases than secondary ones, and that's due to them being less soluble in water. So it just goes a little bit against what we just said here. So if we look, diethylamine with its two alkyl groups is a stronger base compared with ethylamine, which is a primary amine, versus ammonia, which is the weakest base. And that's all due to ethylamine having a greater inductive effect, and then again a greater inductive effect here. The aromatic rings, the aryl groups, withdraw electrons from the nitrogen atom. An aromatic ring next to a nitrogen atom will cause the lone pair to delocalize the rings. What this does is it makes the lone pair less available, so it makes the substance a weaker base. And if we look at these various structures, we know that we're having a positive inductive effect here with our primary amine due to the presence of that carbon-hydrogen chain, making the lone pair on the nitrogen more available. We've got a different layout here. Now here, the aromatic ring, the aryl groups, will start withdrawing electrons from the nitrogen atom in this direction. The electrons from the alkyl groups over here will be releasing electrons towards the nitrogen atom. So if you think about these two effects, they are acting in opposite directions, so they'll actually cancel each other out. And then finally, phenylamine is a very weak base, and that's because of this, the fact that you don't have alkyl groups and the fact that you have your aryl groups, your aromatic ring, actively withdrawing electrons from the nitrogen atom, making that lone pair of electrons less available. I'm now going to draw all the mechanisms for the various reactions. Remember, we are going to be reacting a nucleophile such as ammonia, primary amines, secondary amines, tertiary amines with halogenoalkanes, and we'll be drawing the products that can be produced. These are all examples of nucleophilic substitution reactions. Let's take our first example of chloroethane reacting with ammonia. So you'll have seen this before, but it's the most straightforward example. Our lone pair on our nitrogen attacks the slightly positive carbon, causing the breakage of this bond. Then we have a second ammonia molecule acting as a base because we need to deprotonate here to remove that positive charge, leaving us with this salt. Now remember what I was saying is that this product here, which is ethylamine, can act as a nucleophile too due to the lone pair on this nitrogen. So to make sure that we are making as much primary amine as possible, as opposed to that primary amine getting involved in the further reactions, what you want to do is use excess ammonia. So use excess ammonia to increase the yield of that primary amine. Let's name some things. So that's obviously chloroethane. This is ethylamine. If we didn't have excess ammonia, however, let's actually look at what can happen now. If we take our ethylamine and react it with chloroethane, very similar, just looks slightly more complicated, but our lone pair will attack again at that electron deficient carbon, causing the breakage of this bond. Obviously, our next structure is going to be quite complicated. However, it remains the same that we need to deprotonate that nitrogen. I'm not going to draw this acting as a base here because it makes it really complicated, but remember that deprotonation will look like this. So what's the name of this? It's diethylamine. And then you've guessed it, this diethylamine can now act as a nucleophile. Just keep practicing these until they get so boring that they are so second nature that you know you'll have it sussed for the exam. This is quite a complex structure, but the lone pair on the nitrogen remains the same. It's acting as a nucleophile. So it'll attack here, causing the breakage of this bond. We're deprotonating. I'll need plenty of space for this structure. This is triethylamine. And obviously there's no reason why this tertiary amine can't act as a nucleophile with a lone pair on that nitrogen to attack our chloroethane again. And if that happens, you'll end up with a quaternary ammonium salt. So as you can see here, here's our tertiary amine attacking our chloroethane to produce a quaternary ammonium salt. If we want to increase the yield of quaternary ammonium salt, we want to include an excess of halogenoalkane. Now these quaternary ammonium salts are super useful. They're used as hair and fabric conditioners, and that's because they're cationic surfactants. Remember, a cation is a positive ion. The positive charges of the cations are attracted to the wet surface, forming a coating that prevents the buildup of static electricity. So back in again with ethanoyl chloride. I'm going to be using a nucleophile which is a weak base, ammonia. The lone pair exists on the nitrogen. It's going to attack our slightly positive carbon, causing the breakage of that double bond there. Our oxygen gains a lone pair. The chloride ion is our leaving group, so we need to see the breakage of this bond here in order for the chlorine to leave. The ammonia has added itself. Currently it has too many hydrogens, hence why that nitrogen has a positive charge. So we're going to deprotonate by breaking this bond here to draw a product now. Double bond O here, NH2 because we've deprotonated, and then we have left over that chloride ion again. So to name everything, ethanoyl chloride, here's ammonia, and the name of this substance over here is ethanamide. Now, in these solutions which do contain ammonia, what we find in this situation is that it's another ammonia molecule which removes this hydrogen here, forming an NH4 plus ion, and that's going to react with that chloride ion that left to form NH4Cl. Time for another summary equation. So this time we have acyl chlorides react with ammonia to produce amides. And as I was just saying, ammonium chloride will be our second product. We have our ethanoyl chloride again here. We are going to react with an amine. It has a lone pair on that nitrogen. We are going to attack our slightly positive carbon, causing the breakage of that bond here. Redraw everything carefully, showing that lone pair on the oxygen and the negative charge. We know that we're going to have a positive charge on this nitrogen, two hydrogens attached, plus our CH3. There's our leaving group, the chlorine. Let's add some curly arrows showing the formation of that double bond there, the fact that the chlorine's leaving and that we are deprotonating. Final step to draw the product. We have formed what's known as an amide. Now, the amide functional group consists of C double bond O and an NH. So our summary equation now, we've got our acyl chloride reacting with an amine. It's going to form an N-substituted amide. And then because you've got excess of your amine, that's going to cause the deprotonation here. So you'll end up with an extra hydrogen, and that will combine with your chloride ion to form this salt here. Outline a mechanism for the reaction of bromomethane with an excess of compound J. You should represent J as this. So here's our halogenoalkane. J we know is a primary amine, so we know it's going to be nucleophilic substitution. I don't think this one's too complicated, particularly as we're allowed to represent J as RNH2. That carbon there is slightly positive, that bromine is slightly negative. We have a lone pair on that nitrogen that will attack this carbon, breaking this bond. We need to deprotonate. Compound K is a structural isomer of J. Explain why J is a weaker base than K. So just to bring down that formula of J here. Now, because in K we can see that alkyl group, remember that's going to form a positive inductive effect, meaning that more electrons are released so that that nitrogen's lone pair is more available to act as a base, i.e. to deprotonate.